Hi everybody, today we're going to be talking about mutations, and I just wanted to show you how to get to this PowerPoint. If you are in modules and you scroll down to artifacts from class, you'll see a PowerPoint mutations, and if you blow that up, then you will see this. So a mutation is going to be any change in the letters of DNA. So that means I'm going to be changing a T to an a G to a C, something like that. And it's important to know that modifications to the DNA are not necessarily mutations. So for example, if I don't change a DNA enough to change it from a T to an A, then it's not necessarily a mutation. So mutations actually arise through a sequence of events, and those sequence events are pretty standard, but they usually end up kind of coming from a copying error. So when DNA is being copied, it is being read by a DNA polymerase, and when that DNA polymerase is reading the DNA, if there's structural damage to the DNA, then the polymerase can actually make a mistake. The polymerase also has an error mistake, so just so you know, without any kind of radiation, without any kind of DNA damage, you will end up with mutations in DNA. Most of those mutations, I believe, are caught and fixed. They're fixed in generally about the region of 1 to 1,000. So the important thing is it's the polymerase that actually ends up creating the DNA with the changed base. So let's look at what ends up creating the problem for the polymerase. All right, so I'm going to try to do this animation while I'm talking, and it might be a little bit difficult. What we're going to look at is exactly the part of DNA that's being changed. So let's go ahead and look at all the atoms that are involved here first. All right, let's go ahead and color those CPK. So what you're looking at here is the carbons, the nitrogens, the oxygens, and the phosphors that go ahead and make up DNA. Now let's go ahead and connect them all. That's probably a little bit better. Okay, so what you can see here, or sort of see here, is the double helical nature of DNA, right? So you've got actually two strands of DNA here, and together we call this a DNA molecule. So you have strand 1 right here and strand 2 right here, and if I were to look at them closely, you'd see that they were attracted by two opposing charges right here, and that's called a hydrogen bond, which is actually an intermolecular force and not a bond. You do have bonds in DNA, and you can see them. They occur quite frequently. So that's the literal joining of two atoms by the sharing of an electron. So that's a bond. And to distinguish a bond from a bind, on this diagram you see bonds are generally denoted with a line between two atoms, where a bind, for example in the case here, is not. But when you can see that if there's two parts of this molecule that are basically stuck to each other, they're going to be stuck to each other because there's attracted opposing charges. All right, so let's go back to this PowerPoint. Now, there's generally going to be the two sources of events that lead to mutations. One is going to be the mistake of a DNA polymerase just because of random error. This thing is spinning at about 1,000 bases a minute, so it is working really, really fast. If you measure it or look at it, it looks as though it's a jet engine spinning. And the other is that there's going to be a damage event. Some kind of DNA damage is going to happen, whether that be alcohol or a mutagen or gamma radiation or X-ray radiation or UV radiation. That's going to damage the DNA, and in an attempt to fix that DNA, the polymerase is going to make a mistake. So let's go ahead and look at the situation in which the DNA is mistakified. So here what you see is UV radiation. So UV is electromagnetic radiation, and basically it's going to hit this molecule here and it's going to kick off some electrons, and those electrons getting kicked off are going to cause the formation of some weird bonds, and those weird bonds are going to end up kinking or causing a problem in the DNA. Here you see this. This is a UV light which specifically affects thymines, and it causes thymines to kick off electrons and then bond to each other, especially when they're right next to each other. And what can happen is that when this thymine dimer is being copied, if it is not caught, then the DNA polymerase can actually put in mistake letters in the meantime. But what usually happens is that there's going to be a repair mechanism. So there's going to be an enzyme that comes in, makes small cuts in the DNA right here, takes out a piece, and then replaces it with a complementary sequence to this piece right here. So let's go through those events again. We're going to have a reactive species, an oxidative species, UV light, gamma radiation, X-ray, alcohol, a bunch of different things that can cause mutations. So those are going to be called mutagens. They cause some kind of change in the DNA. Generally, that forces some structural change in the DNA, and most of the time, those things are going to be caught and repaired. However, if they're not caught and repaired, then they can make it through as a mistake in the DNA. So for example, you might see a T here and then an A here, and the A would be a mutation. Now, the most dangerous kind of DNA damage is what is called a double-stranded break, or a DSB, because scientists are cool. So here you see we have a single strand that is still intact. We cut out the part of the strand that was like looped with the thymine dimer. So we knew what to replace this strand with right here. However, if both pieces were missing, then it would be difficult for the DNA polymerase to lay down a correct sequence in its place. So anything generating DNA damage is going to be dangerous, especially if it causes like these kinds of bowing out systems. But any kind of double-stranded break is going to be super dangerous. So let's go ahead and metaphoricalize that whole thing. So let's say you have DNA, RNA, and a protein. So that in our metaphor is going to be Auntie Drudge's cookbook. Our RNA is going to be Elaine's green mashed potatoes, and then our protein is going to be the potatoes themselves. So what we would end up with in the case of like X-ray radiation, for example. Imagine when copying, and when we take Auntie Drudge's cookbook, and in Auntie Drudge's cookbook we nail it with some X-ray radiation, and then what it basically does is it smudges out the P in potatoes. So when we go ahead and copy the mRNA here, this potatoes is kind of messed up. And instead of potatoes, it looks like tomatoes. So then when the chef gets this recipe, instead of making mashed potatoes, he makes mashed tomatoes, and then realizes that he's got to make deep dish pizza with it because deep dish pizza is awesome.